Okay, so in this video, I'm going to explain what bases are and basis transformations and why they're useful. I'll explain why they're useful in the SVD video, but in this video, I just want to drive home the point of bases and how to transform vectors from one basis to another. Now, let me just put an example. Let's say that I work in the Cartesian coordinate plane. I'm sure you all know what the Cartesian coordinate plane is, right? Where you have x and y and you have 1, 2, 3, 4. Similarly, you have y, your normal x and y axis. That's a Cartesian plane. Okay, this is the plane that I work in. Now, let's say my friend works in a different plane. Maybe he works with polar coordinates, r sine theta, r cos theta. All right. And let's say I have a point in this plane. This is 2 comma 2, and I want to convert this to the polar coordinate plane, right? Now, obviously, I can't just take 2 comma 2 and just put it here because there are some rules for conversion from a Cartesian plane to the polar plane. And unless I follow those rules, I can't just take this point and put it over here, right? Um, so similarly, when you move from the Cartesian coordinate plane and the polar coordinate plane and you come to matrices, what happens is generally people work with, uh, you know, uh, the normal bases, which is 1 comma 0 and 0 comma 1, right? This is x and this is y, correct? And similar to this, like let's assume that this is equivalent to the Cartesian coordinate plane. But it can so happen that someone else, maybe my friend, doesn't work in x1, doesn't work in this normal basis. Maybe he works in a different basis. Maybe his basis is defined by something like 1 comma 1 or 1 comma minus 1, right? Maybe he works in this. So if I have a vector 1 comma 2 in my basis, how do I transform this vector and find its value in my friend's basis? His basis defined by 1 comma 1 and 1 comma minus 1. Now, obviously, like you can't just copy paste a point from Cartesian to polar. You can't copy paste a point from one basis to another, on one basis to another. There are some transformation rules that I will derive the transformation rules first so that it's easier to understand. Think of this as, transforming from one language to another. I speak this language and my friend speaks this language. If this is a word in my language, I can't just take that word and put it in his language because he won't understand anything. I'll have to translate this word into a different language. And what are the rules for the translation? I'll explain now. There's a derivation coming up. And after this derivation, you should understand basis transformation very well. I'll also explain this with an example. I'll take the same example that was given as the question in the first pop quiz. So, okay, so let's say I have two bases, E1, which is my x-axis basis. It's defined by, it's defined by 1 comma 0. Okay. And then I have another basis, E2, which is my vertical or the y-axis basis, which is defined by 0 comma 1. And this is E1, this is E2. And let's say I have a point here. Let's call this point 1 comma 2. Okay, this is a vector. Every vector every vector in this space can be expressed as a linear combination of E1 and E2. If I call this vector W, I can express W as 1 into E1 plus 2 into E2. Okay, this is similar to 1 into 1 comma 0 plus 2 into 0 comma 1, which is essentially 1 comma 2, right? You just multiply 1 and 2 here and you just add them. Now, let's say that I have a different matrix plane. which is defined by different bases. Let's say one of my bases is, let's call it 1 comma 1. Let's call this 1 comma minus 1. Okay, it's basically vertical. I'll erase this. One comma 1 and 1 comma minus 1, right? This is the basis A and this is the basis B. Okay, I'm just giving it a name. Now I have a vector in my A basis which is defined by 1 comma 2, and I want to translate this vector into the basis B. How do I do that? Let me derive how the steps of how to go about it over here. So let's say my basis A, which is this one, is defined by two bases, A1 and A2. Consider these equivalent to E1 and E2. I'm just taking A1 and A2 because it helps the derivation. But A1 and A2 is equivalent to E1 and E2. Okay. Similarly, I have my bases in the matrix world B, and this is defined by B1 and B2. Okay. So now to translate this vector into this matrix world of these bases, I can write B1 as a linear combination of some constant into the bases in the A world. All right. So I'll write this as x11 A1 plus x12 A2. This is B1. Similarly, I'll write B2 as x21 A1 plus x22 A2. To transform this vector into a vector in these bases, I have to make sure that B can be written as a linear combination of the bases in A. If that can't be done, I can't translate this vector because ultimately it has to be a linear combination, right? And let's say I have a vector V, okay? Let's say I have a vector V in the basis B, right? And this vector in the basis B can be written as a linear combination of B1 and B2, right? So I'm going to write V as a linear combination of B1 and B2. V1, B1 plus V1, B2. Okay. So now what I'm going to do is I'll come here and I'm going to expand this. I'm going to write V as equal to V1 x11 A1 plus x12 A2 plus V2 into x21 A1 plus x22 A2. Okay, that's all I've done. I've just taken this from here and I've just substituted the values of B1 and B2 over here, right? And what this essentially is, if you solve this further, you will get V as V1 x11 plus V2 x21 A1 plus V1 x12 plus V2 x22 A2. Okay, if you solve this further, you'll basically just get this. Now I can write this in a matrix form, right? I can write this as, do I have more space? Yeah, I have a little more space. So I can write this as, in matrix form, I can write this as V11 x1, V2, it's V1 x11, V2 x21, V1 x12, and V2 x22, right? This is equal to the coefficients of the vector V in the basis A. Okay. Wait, I'll just go to the next page. I'll write it again. V1 x11 v2 x2 1, v1 x12, v2 x2 2. This is equal to the coefficients of the vector v in the basis a. Okay, the the vector v, this one, in the basis a, right? If you just solve this, convert this into the vector in the matrix form, you'll get this. Okay, so this can be written as x11, x21, x12, x22 into v1 and v2 is equal to the coefficients of vector v in the basis a, right? So what is this? This is basically, what is x11, x21, x12, x22? If you look carefully, x11, x21, x, all of this, right? This is just the coefficients of the basis b and the basis a, right? So I'm going to write this as coefficients of b in a, and this is the coefficient of the vector v in the basis b, coefficient of the vector v in the basis b. And this is equal to the coefficient of the vector a, vector v in the basis a, right? So what is this? I'm going to write this as x because this is very easy to find out. So this is basically x vb equals va, and I have the value of x. I need to find the vector v in the basis b. If this is the vector 1 comma 2, I need to find what is its point in the basis b, considering that I have a vector representation in basis a. So simple, I'm just going to multiply this by the inverse. This becomes identity vb equals x inverse va, which is equal to vb equals x inverse va. Okay. So at this point, I will urge you to just write the derivation on your own in a paper and go through it once again. And the next video, I'm going to explain using a question how this works. All right.